Good afternoon. My name is Hoang and Thinh. My student ID is s4113609, and this is my presentations about assignment 1. The assignment has 3 questions: a one-round key, AES 128, the PKCS number 1, and the ECC NIST P-256 signatures verifications. The array value I showed today, the key, the plain text, the RSA exponent, and the ECC private key comes directly from my old student ID and email address. So the numbers are specific to me. Now, let's begin with question 1. What I need to do in this step is to generate a 16-byte key and 16-byte plain text block. The task fixes how I must build bar from my old identity. The K comes from my first 16 characters of my RMIT email. The P's come from my name and student ID with leading S removed. What I need to do in this step, the deriving K and P from my personal data means the entire round of encryptions that follows is unique to me. Nobody else submissions produce the same state matrix, so the workings cannot be just copied. In this here, the hex, the plain text, and the serial key is generated into the hex decimal. In question 1, task A, the round 0 key is simply the original 16-byte key, so no key expansion is needed here. I place the bytes into a 4x4 matrix, column by column. This order matters because all later AES operations use the bytes position in this state matrix. For questions 1, task B, the initial transformation is AddRoundKey using this formula. I will walk through position 0, which is P0 4A, KO is 73. So in the binary, it's here. So I will show it. It gives the output binary and 39 in hex. The remaining 15 positions use exactly the same bitwise sort, and the full table is in the appendix. The reason this step matters is that the sort is its own inverse. So decryption reuses the identical operation, and critically is the step that ties the output to the serial key. Without it, the cipher wouldn't depend on the key at all. The resulting state 0 matrix is what fits into the SubBytes next. Now, let's begin with question 1, task C. What's this step about? Every byte of state 0 is replayed independently using the fixed FIPS Xbox. The first value of the byte select the rows, and the second value select the column. For example, in the first byte here, I choose 39, and it will select the row 3, column 9. I will look up into the Xbox 39. In here, the row 3 and the column 9, it will generate into 12, so that the remaining 15 values here will be use the same method. In question 1, task D, ShiftRows. So what is it about? Each row R is cyclically shifts left by the R positions. For example, row O unchanged, row 1 shifts by 1, row 2 shifts by 2, and row 3 shifts by 3. Why do we use the ShiftRows? The MixColumn in the next step only mix the bytes within one column. Without the ShiftRows, the 4 columns would behave as 4 independent 32-bit ciphers. The ShiftRow force diffusion across the whole block. So, for example, before ShiftRows, the first variable is number 12, so it is unchanged. For the row number 2, the first variable is 39. So after the ShiftRow, the 39 into the last places. For the next 2 variable in row 2, it will go to the last 2, and the same thing with the row 3s. With 3 bytes, it will convert into here. Questions 1, task E. MixColumns multiplies each shift column by the fixed matrix shown. The calculation takes place in GF2 to the power of 8. Multiplications by 0 to use a left shift, and when needed, reduction with 1B. Multiplications by 3 equals multiplications by 2 short the original bytes. This creates diffusion. Why do we use the MixColumn? MixColumn is what gives AES diffusion within a column. A 1-bit change in any input bytes change all 4 output bytes of that column. The small differences spread rapid across rounds. As a general example, 02 multiplied by E2 gives DF after shifting and reduction. For the actual first column, the first output is 02 times 12, so 03 times CB, so 4A, so 4C, giving 64. The same linear combinations method applies to to the other 3 bytes of column 0 and to column 1 to 3. This 16 byte states is the final answers required for question 1. Question 2, move to public key encryption. Why I need to do this step? Because E must be the largest prime factor, not a conventional value. So this key pair is briefly tied to my old student ID rather than a generic template. I factorize my student ID as 3 times 17 times 79 times 1021. The largest prime factor is 1021, so it becomes the public key exponent. Let's continue by generating the modulars and the private key. In this step, the primes P and Q were generated ultimately using these tool. So I can calculate the N and the modulo using these two formula. So I can get the N and the D here. So by default, the public to users is the N and the E, and the value that is secret to the server is the D, the P, and the Q. This diagram is the overall process of login information protection. What I need to do first is, before sending, I convert the payload to hex, treat it as a single large integer, then encrypt it using this formula and the cloud public key ENN. Why do I use this? Because encryption with the public key gives confidentiality against eavesdropping. Anyone can encrypt, but the only holder of D can decrypt. What I send to the server is only the ciphertext. The plain text credentials never travel on the wire. The login payload here includes my student email, my password, and the timestamp. First, I will convert it into the hex encoding of M. So I got this hex is 7334 3039, and then I use this formula with the public exponent. Then I get the ciphertext here, A2F1 79778. So this ciphertext will be sent to the server. After the server receives the ciphertext, it will reverse the encryption using its private key. Using this formula, then decodes the hex back to ASCII. So as you can see here, it's this formula, and then the result it will receive is the matches original hex that we have before. How do the server do this? The server's private exponent and the share modulars are only the values needed. The same modular exploitations routine runs in reverse. Why do we use this? The decryption recovers confidentiality, but the server still needs the password and the timestamp checks. Decryptions alone does not prove who sends the message. So as you can see here, it will convert the hex into the plain text again, and we will get this one. So the server will check the password with the database and the timestamp check against the server clock. In the previous part, RSA protects the confidentiality of the login data. The final question addresses a different objective, proving that an instant identity document was signed by AWS and was not modified. What we need to do is check that the given point X and Y satisfy this formula. So on the left-hand side, we have this formula, and on the right-hand side, we have this formula. If the two results is matches, we will conclude that the generator point lies on the AWS P-256 curve. So as you can see here, to the result match together. The private key is my student ID, and we will calculate the public key Q using this formula. So my private key, and then we have the public key QX and public key QY. Why do we use this? Because the D must stay secret. This formula is published so everyone can verify AWS signatures without ever learning the D. This session is about signing the instance identity document. To sign the document, first, I hash it into SHA-1 as required and convert the hash into the integer Z. I choose the temporary key K as this number. The first signature value R comes from the X coordinate of K times P modulo Q. And then I have this result. The second value S is K inverse times Z plus R times D modulo Q. And then I will receive this result. The signature is the pair R and S. The value K must be unique and secret. After I have the signature, this will be sent to the user alongside the plain text instance identity document. Question 3, task 4. What we need to do in these steps is that the verifier recomputes a point using only public information, the hash R, S, and public key Q, and checks whether its X coordinate matches the R. And then how do we use this? The verifier hash the document again and calculate the W as the inverse of S. Next, U1 and U2 are calculated from the hash R and W. These values reduce a new elliptic curve point using the public key. Its X coordinate gives V. Because V equals R, birth beginning with 1640, ending with 1422 in this here. So we can conclude that the signature is valid and the document is unchanged. In summary, the three techniques solve different problems. AES demonstrate confusion, diffusion, and key dependence within a single shared key route. RSA protects the login data confidentiality, but needs a separate application layer defense, for example, password and timestamp, for authentication and threadness. ECDSA lets anyone verify the AWS instant identity document publicly without ever exposing the private key. Together, these three questions show how symmetric encryption, public key encryption, and digital signatures protect different parts of cloud communication. So the previous slide is the last slide of my presentation. Thank you for listening.